So we will be graphing functions. This is just review from algebra to pre-calculus, and these are important graphs that will come up this year. So we want to make sure we can graph these quickly. So starting with ln x, so that's simply log base e. And we always want to start with our vertical asymptote and our locator point. So with a log graph, as long as there are no horizontal shifts, the vertical asymptote will be located at x equals 0. So there is a vertical asymptote here. So make sure you have that marked on your graph. And then the locator point, as long as there are no horizontal shifts or vertical shifts or stretches, is going to be at 1, 0. So if there are any stretches or shifts, like if there are any transformations, that will change this point. But this is a good, it's almost like a vertex, but it's not a vertex because a vertex is where two sides meet. So this isn't really a vertex, but it does give us like a point to always start at. And then from there, we can move it along with any transformations. And then a log graph is going to approach the horizontal asymptote, pass through the point, and then go off like this. It does go up forever, so the range is from negative infinity to infinity, but it doesn't go up very quickly. So remember, this is the inverse of an exponential function, which does generally go up very quickly. Now, if you want to plug in points, because I said make t-charts if you need to, just make sure that you plug in points that are easy. So for example, if I took ln of e, and e is about 2.718, if I did ln of e, I would get 1, right? So that's 2.7181, and so I do have like a point here. So if you wanted to get even more precise, you could plug in a couple points. With ln, it's not so easy without a calculator, and you should be able to do this without a calculator. So I would expect to see like the locator point is specific because ln of 1 is equal to 0. Log base anything of 1 is equal to 0. So the locator point is important. It's usually the easiest one to plug in because log base anything of 1 is equal to 0. And then your vertical asymptote should be clear in your graph as well. Okay, the square root of 16 minus x squared. This one is going to come up a lot this year. Comes up a lot. And it's not something that we necessarily have memorized, but if you start plugging in points, you're going to figure out what it's going to look like. So if you plug in 4, for example, so just start plugging in easy numbers. If I plug in 4 squared is 16. 16 minus 16 is 0. The square root of 0 is 0. So if I plug in 4, I get 0. 1, 2, 3, 4. I get 0. If I plug in negative 4, same thing. Negative 4 squared is 16. 16 minus 16 is 0. So 1, 2, 3, 4. Negative 4 is 0. If I plug in 0, 16 minus 0 is 16. So if I plug in 0, I get 4. And then I can't plug in any numbers greater than 4 because then I'd be taking the square root of a negative. That's not allowed. I can't plug in anything less than negative 4. So I can only plug in numbers from negative 4 to 4 anyway. And what this ends up looking like is it's actually a semicircle. And it is only a semicircle. We're not going to graph down here. It's not, doesn't break the rules of a function, okay? It is a function. And the reason that you don't graph down here is because there is no plus or minus. If this was negative square root, then I would only graph down here. But because it's a positive root, then that's going to give me positive values only. So I just want to point out, you might want to like highlight this or something. That one comes up a lot throughout the year. And I will tell you constantly, hey, take out your notes. You need to go back to review this graph. Okay, x equals y squared. So we know what y equals x squared looks like. Y equals x squared is a parabola that faces up. So what is x equals y squared? Well, x equals y squared is a parabola, but it's not a function. Our independent value ends up being y in this case, and our dependent value ends up being x. So if you want, just start plugging in numbers. If I plug in y equals 0, I get x equals 0. If I plug in y equals 1, I get x equals 1. If I plug in y equals negative 1, so negative 1 for a y value, I get 1 for an x value. If I plug in 2 for a y value, I get x equals 4. If I plug in -2 for a y value, I get x equals 4. So it's kind of backwards. If you need to, make a t-chart. But basically, x equals y squared is very similar to y equals x squared, but it kind of faces sideways. So if you think about it, it reflects over the line y equals x. So it's kind of like the inverse of y equals x squared. It is the inverse, but it's not a function, you'll notice. So x equals y squared is not a function. So I just want to point that out. Because you're plugging in y values and getting 2 different y values and getting the same x value, that means it is not a function. And that's okay. We're going to be dealing with stuff that aren't functions this year as well. F of x equals the absolute value of x over x. So again, this isn't one that you necessarily have memorized as a parent function, but this one comes up a lot throughout the year. So I just made a t-chart for you over here. If you plug in -2, for example, the absolute value of -2 is 2. 2 divided by -2 is -1. If I plug in -1.5, absolute value of -1.5 is 1.5. Divided by -1.5 is -1. You can kind of start seeing a pattern here. If I plug in -0.3, the absolute value will be positive 0.3. Divided by -0.3 would be -1. And then if I plug in 0.1, so positive number, absolute value of 0.1 is 0.1. Divided by 0.1 is 1. If I plug in 1, absolute value of 1 divided by 1 is 1. The square root of 319, the absolute value of root 319 divided by root 319 is 1. So if I start plugging these points, so -3, -1, -2, -1, -1.5, -1. So all of these values, until I reach 0, are going to be -1. Now I'm going to put a hole here, because if you plug in 0, you get 0 over 0. And as you know, that does not exist. And 0 over 0 specifically is going to give me a hole. So I'm going to go ahead and jump up. So at 0.1, we're at 1. At 1, we're at 1. At root 319, wherever that is, that's going to be y values of 1. So I am going to have a hole again at 0, 0, and then, oh, that's not great. Let's try that again. There we go. And so that's what the absolute value of x over x looks like. So again, these types of functions come up. It might be absolute value of x over x, or it might be x over absolute value of x. But just know it's going to be 2 horizontal lines with a hole, or a jump discontinuity, as we call it. All right, now this one you might not have seen before, and that's okay. So this will come, I don't know why I keep saying that. This will come up this year. That's why we're learning this. So the greatest integer function is when you round down any fraction or decimal. So if it's a whole number, it stays a whole number. So 3 goes to 3, 2 goes to 2, 1 will go to 1. Okay, so whole numbers are going to be what they are. So I have 3, 3. So 3, 3, I have that point. I have 2, 2, I have that point. I have 1, 1, I have that point. But what happens at the non-fractional values? So they round down. So 2.9, although it's very close to 3, rounds down to 2. 2.5 rounds down to 2. 1.99, very close to 2, but rounds down to 1. 1.6 rounds down to 1, et cetera, et cetera. So if it's a fraction or a decimal, you need to round it down to the nearest whole number. So 0.99 is close to 1, but we know it rounds down to 0. 0.5 rounds down to 0. 0 stays 0. Negative 0.1. Now, this is where students get confused with the negatives. Okay, negative 0.1. If you think about a number line, okay, so we have 0 here. We have -1 here. Negative 0.1 is here, okay? Where does it round down to? It rounds down to -1. Negative 0.9 rounds down to -1, and then -1 gives me -1. So what this looks like is this. So I have 2.9, so 2.9 right about here, comma 2. 2.5, comma 2. Any number between 2 and 3 is going to be y values of 2. So it ends up looking like this. But then at 3, it jumps up, right? So it's just going to follow this pattern as you graph. And these steps, I'm not going to do every single one of them, but it does go on forever and ever, okay? So it goes on in each direction, this direction, this direction. But basically the value is, if I have negative 2.5, that's going to round down to negative 3. And if I have 5.5, that's going to round down to 5. So if you have the greatest integer function, you might need a t-chart, or if you can remember that it's like a step function, it does have a filled in dot on one side where your integer values are, but then on your step, the other side is going to be a hole because we have to jump up to the next step. And this is a function, you'll notice it does pass the vertical line test. All right, sine x. So you should remember this from pre-calculus and algebra 2. So I'm going to go ahead and just go by 2 pi's. And you always want that to be in quarters because we've got 4 quadrants going around the unit circle. So sine of 0 radians. So just a quick review of unit circle stuff. Sine is the y coordinate. So we're going to start at 0 radians and then go counterclockwise. So at 0 radians, what is the y coordinate? It is 0. I'll call this 1. And I'll call this negative 1. At pi over 2, what is the y coordinate? It's 1. So pi over 2, my y-coordinate is 1. At pi, my y-coordinate is 0. At 3 pi over 2, my y-coordinate is negative 1. And then at 2 pi, my y-coordinate is 0. And then it's cyclical, right? The period is 2 pi, so it repeats itself. And it's just going to look like this. And we could get more precise and start graphing like pi over 6 and pi over 3 and all that fun stuff. But you don't need to do that. As long as you know your maxes, mins, and zeros, you should be all set. Cosine, likewise. Cosine is the x-coordinate. So starting at 0 radians and moving clockwise. So 2 pi, 1, negative 1, negative 2 pi. If I start at 0 radians, my x-coordinate is 1. Going up to pi over 2, my x-coordinate is 0. Going to pi, my x-coordinate is negative 1. At 3 pi over 2, my x-coordinate is 0. And then at 2 pi, my x-coordinate is 1 again. So we just repeat that. The period is 2 pi, so it just keeps repeating itself, etc., etc. And our graph looks like this. So again, maxes, mins, and zeros are what I want from you. You should have the other parts of the unit circle memorized, but when you're graphing, maxes, mins, and zeros are all we really need. All right, and then our last two. So we've got a polynomial here, and I did tell you to factor first. And that's pretty much always a good rule, is if you are graphing a polynomial, you should try to factor it first. If you need to, you might need to use like synthetic division to test zeros along with the rational root theorem. But you should always try factoring first because that's going to be a lot quicker. Okay, I noticed that I have 4 pieces and they all have an x squared in it. So I'm going to go ahead and factor out an x squared. So that's going to be x to the third plus 3x squared minus x minus 3. All right, it's not factored all the way. So now I see I have 4 pieces. These 2 pieces I could factor out an x squared from, and these 2 pieces I could factor out a negative 1. So this is called factoring by grouping. So from the first 2 pieces, I can factor out an x squared, and I'm left with x plus 3. And then my last 2 pieces, I can factor out a negative 1, and I'm left with x plus 3. Oh my goodness, I have x plus 3 and x plus 3. So what can I do when I have, what I do now have is 2 big groups, and they both have an x plus 3. So now I can factor out an x plus 3 because they both have an x plus 3. So I'm factoring it out. And what am I left with? X squared minus 1. All right, and then x squared minus 1, you should recognize, is a difference of squares. It's x plus 1, x minus 1. So we have zeros at 0, negative 3, 1, 2, 3, negative 1, and 1. All right, now because this is a positive x to the 5th, that means we're going to start up here in positive land. If it was negative x to the 5th, it would start down here. But it's going to start up here, and then we're going to pass through 1. Now, we have to go back to 0, but because it has an even multiplicity, that means there is a bounce, which means it's not going to pass through. It's going to bounce off. And then I have a 0 at -1. That one I just crossed through. And then I have a 0 at -3, and I just crossed through. And notice that I'm not like plugging in other points. I don't care about that. I just need a general shape. I need your end behavior to be correct, and I want your zeros to be correct. And that's what's going to be, we're going to do a lot of graphing this year. That's what's going to be important. Zeros are correct, and end behavior is correct. All right, and then lastly, number 9, we have holes, x-intercept, vertical asymptote, horizontal asymptote. So this is a rational function, and we've got a bunch of stuff going on here. It's already factored. If it wasn't, I would tell you to factor, but it's already factored. Now, you might want to just cancel those and then ignore it. But although we are going to basically cancel it, what this tells me is that this is the graph of negative x over x plus 3 with a hole at x equals 2. So if you are going to cancel a factor in the numerator and denominator, just remember that's going to be a hole. Now, what is the exact coordinate? So I know it's going to be at x equals 2, but what's the other coordinate? Well, plug in 2 into your simplified answer, negative x over x plus 3. So that's going to be -2 over 2 plus 3, so -2/5. And that gives you the y coordinate. So in order to find the y coordinate, plug the x coordinate into the simplified result. The coordinate of your x-intercept. So where does this graph cross the x-axis? So again, we basically simplified this now. We can ignore the hole. So as long as the hole doesn't stick around in our simplified result, we are not going to take it into account anymore. It's not also an x-intercept in this case. It's not also a vertical asymptote. It's gone. So now, after I've noted my hole, I'm just going to look at what I have. So I have negative x on top. So what makes this function 0? Well, if I plug in 0, I get -0 over 3, and that gives me 0. So I have an x-intercept of 0, 0. Because that's what makes my numerator equal to 0. That's where my zeros are. What makes your numerator equal to 0? And then your vertical asymptote is what makes your denominator equal to 0. And that would be x equals -3. And it is an equation. It's not a point. It is an asymptote, so it's a line. And it's because if we plug in -3, we get 3 divided by 0. A number divided by 0 is generally a vertical asymptote, and especially for rational functions like this, if it's a number divided, like a non-zero number divided by 0, that's going to be a vertical asymptote. And then a horizontal asymptote. So what happens for a horizontal asymptote? That is what happens as x approaches plus or minus infinity. So if I plug in a really big number, what happens? So that would be -infinity over infinity plus 3. Okay, well, infinity plus 3 is basically infinity, right? If I'm a bazillionaire and you hand me $3, that makes no difference. I'm still a bazillionaire. So I can basically ignore the plus 3. I can kind of ignore it. Now with like squares, like if I had a power, I would not ignore that power. But when you're just adding or subtracting numbers, it really doesn't make a difference. So then I get -infinity over infinity. So what does that approach? -1. Another way to think about it is that the powers match on top and bottom. So you can divide them. -x over x is -1. So that might be the rule that you learned last year. All right, now horizontal asymptotes only exist at the ends. So I do not want you to graph them all the way through because this is end behavior, not middle behavior. So I don't even draw it in the middle because it's just end behavior. Your vertical asymptote is at x equals -3. You have an x-intercept at 0, 0. You have a hole at 2, -2/5. So that's like, I know it doesn't have to be exact, right about here. Okay, and then how do we graph this? Well, you're going to follow your end behavior. It doesn't matter if you're on top of it. It doesn't matter if you're below it or above it. It just needs to be near because it's approaching. So we're approaching our horizontal asymptote. And then we hop over the hole. We pass over the bridge, our x-intercept. And then, oh, look, we have a vertical asymptote. So I'm going to go up. Notice that I did not start going down. I can't like change direction because I don't have a bridge here. So you cannot cross the x-axis. I always call the x-axis like the river Styx. It's like if you cross the river Styx, you die. So don't cross the river Styx without a bridge. We have a bridge here. Our x-intercept is 0, 0, but you cannot cross the river, cannot cross the x-axis anywhere else. So our only choice is to go up. Okay, now vertical asymptote is a magical infinite wall. So when you end up on one side, it magically transports you to the opposite side. And then I look for more bridges, no more bridges. So I have to just approach. Again, doesn't matter if you're above or below or on your end behavior. It's just near it. It's like a fence. Like I can climb on top of a fence if I want to, as long as I'm walking next to the fence. It doesn't matter if you're above, below, or on top of it. It's just a little fence. Now, my magical infinite wall, I am not allowed to cross. So you are not allowed to cross vertical asymptotes, but horizontal asymptotes work slightly differently. All right, so that is the graphing that I expect you to come into this class generally knowing. Again, some of these you would not have had memorized or maybe have not seen before, and that's okay. So like the semicircle, absolute value of x over x, greatest integer function. It's okay if you haven't really seen those before, but they will come up a lot this year. You should know some basic trig. You should know polynomials, and you should know rational functions.